Okay. All right. Good morning. Welcome back.
Hey,
Good morning.
Okay. This lab you should find pretty easy to do. You're gonna do the ballistic pendulum, and it's going to take you through the ballistic pendulum problem. Now, this is one of actually my favorite labs for a in-person style lab. Especially back in the days when I remember many years ago taking physics, because we did real ballistic tests with rifles in the lab and all of that sort of thing. But what we have here is a simulation of the pendulum. I put down some of the basic things you need to worry about. I put down your background equations on this particular one, although we have finished the chapter. Remember that momentum of a particle is mv. The sum of the forces is delta p over delta t. The impulse of a constant force is delta p. And you're going to need to take a look at these problems and analyze the force imparted on an object and the average force, making a couple of assumptions. So some of the problems have you making a couple of assumptions so you can calculate what the average force imparted on the block is and things like that. With a ballistic pendulum was a pretty ingenious yet simple and elegant apparatus invented back in the mid 1700s. And this was used because there was no good way to measure the velocity of a bullet or a high-speed small projectile. Now, in our modern day, where we have laser beams and able to use timing mechanisms through by crossing laser beams and all sorts of fast timing mechanisms, it's now obsolete. But in its day, it was not obsolete. It was the only way to really do a good measurement of a high-speed projectile. Now, some simple examples of projectiles that you'd use for this would be a baseball thrown by a pitcher, a spear thrown by early hunters, arrow launched by a bow, ball launched by a compressed spring, a bullet fired by a gun, just to name a few. And the primary use of the ballistic measurement was to measure high speed, low mass objects, such as a bullet fired from a gun or a rifle. And having them have impacts that were completely inelastic, with a much heavier object. So I take a light, fast object impacting with a stationary object, a stationary high mass object, and then I measure the velocity of the combined pair afterwards and use conservation of momentum to get the velocity before impact, the velocity of the bullet before impact. Now, measuring the velocity immediately after impact itself can be difficult to use that conservation of momentum, and there's a clever apparatus that was developed called the ballistic pendulum. And here is a picture of ballistic pendulum. So before collision, we have a block hanging from, say, a couple of ropes or a single rope, but usually a couple of ropes, and a bullet that comes in. It embeds itself in this, say, block of wood. So that's a completely inelastic collision, and we assume that this collision happens over a very short period of time, because that could be one of the errors by it taking too long of a time. And then the pendulum moves up, and we have some maximum motion of the pendulum. So we want to measure its height. Now, in practice, at the original ballistic pendulum, you would have actually a slider put right here, and you'd measure the horizontal distance that it moved, because that would fix the horizontal distance, give a nice measurement, use some trigonometry then to determine the height. But in this particular simulation, we're just going to measure the distance using the simulation itself. During this impact, we have conservation of linear momentum. And after impact, in this area, we have conservation of mechanical energy. We're going to assume there's no friction present. Again, friction would be one of the sources of error in this. Other sources of error that we haven't really gone into it before would be, say, something like if we don't impact this at normal to the surface. If I impacted it going up, it's going to then impart an initial velocity up, as well as an initial velocity in the x direction. In addition, if I impacted it, say, coming from behind the page to into the page, you're going to put some of that energy into angular momentum or rotation of the block. That's a hint on where some of the sources of error are. Because there's a question about sources of error, asking to list error, source of error. By measuring then the maximum height that the pendulum swings, we get to determine the velocity that the block and the bullet had after impact. So we've got a situation here. We've got the kinetic energy of the bullet beforehand, which is 1/2 mass of the bullet times the velocity of the bullet squared. And the momentum of the bullet is equal to the mass of the bullet times the velocity of the bullet. After impact, which we'll call A sub I, we have a velocity of the bullet block pair after impact. But it's completely inelastic, so we have the mass of the block plus the mass of the bullet, capital M being the mass of the block, as listed here. So the kinetic energy after impact is 1/2 mass of the bullet plus mass of the block times the velocity of the bullet block pair squared. And the momentum is equal to the mass of the bullet plus the mass of the block times the velocity after impact. Now, the momentum before collision has to equal the momentum after collision. The kinetic energy before collision does not equal the kinetic energy after collision. Okay, it's completely inelastic, so those are not equal. But momentum is always conserved. So the momentum before collision and after impact is conserved. But after, once this starts going, the block has some kinetic energy, and there's only conservative forces acting on the block. We're assuming friction is 0, so we have no non-conservative forces. So there's conservation of mechanical energy, and this kinetic energy, so this velocity is still difficult to measure, okay? But the final potential energy is not so difficult to measure. So we have the bullet block pair, the center mass, and it raises to some height at the maximum height of the pendulum. So at maximum pendulum motion, it's reached some height, and our potential energy max equals mass of the bullet plus mass of the block times G times H, and that has to equal to 1/2 mass of the bullet plus mass of the block times the velocity after impact squared. So we can get the velocity of the impact squared. Hence, we can get the velocity after impact. Then we can use our conservation momentum to get the velocity of the bullet. So all of that is a very straightforward set of exercises. You should not have any problem with that. I'm not going to work out. I'm going to go ahead and show you the simulation. I'm going to ask you to just work this honestly and turn off show initial velocity of the bullet. I'm just going to ask you to have that off. Okay? I can't keep you from turning it on. You can turn it on later, check your work, but you need to show your work in this lab. Okay, now there's a table in here that you're going to fill out. You're going to do a few different tests of this. Okay, we're going to start with some different masses of the bullet, where you can change the mass of the bullet here. I want you to do it at 0.5. That's all the way to the left. I want you to do it at 0.1. That's all the way to the right. And at 0.75. That's right in the middle. 0.075. Now, these are in kilograms. So we have 50 grams, 75 grams, and a 100-gram bullet. That's the mass of the bullet. I'm going to use a mass of the wood block, 3, 4, and 5. Okay, that's done over here. 3, 4, and 5. And you see it actually makes the block look longer or shorter. Okay. Now you have a height ruler here. You can start it right at the center if you want, or you can start it at the bottom. I suggest you start it at the bottom, or you start it at the top, one or the other. But the top is going to have more difficulty because this only goes up so high. Okay, now I ask you to set the velocity of the bullet approximately 2/3 of the way of maximum. So this is about 2/3 of the way. I'd call that about 2/3 of the way. Doesn't need to be exact. And you hit fire. Now, the joy here is that this just keeps swinging freely because there's no friction. In a real world experiment, you would have friction, and this would be damping. It would damp out, which is why what I told you before, if you did this in the lab, and we had a mechanical lab and early experiments of this for firing a real gun into a block of wood, I'm giving you more information than you need, had a slider right here and a sliding scale that was slid along a scale. So we'd see how far it moved after impact to the right, and you use trigonometry to get how high it went up. Because it would just be 1 minus cosine of the angle, okay, equal the height. We already had the length, and we have so we'd have L times sine theta equals the height. So we could get equals the length here that it moved. So then we could get theta, and then L cosine theta. We'd use that in the expression of 1 minus L cosine theta, or L times 1 minus cosine theta to get the height, like we've done in some other things. But in this simulation, you're just going to use the slider to get the height. So you're going to move this up and down. So I see that I'm still coming up higher than that. Don't seem to come up quite that high. And it's somewhere right around there. So I have an H of about 0.4 meters. This will do up to 2 significant figures for 2 decimal points. So I'd write 0.40. And I would take that for there. So maximum height of the pendulum, you fill in here. You can now write what is the potential energy. You have a mass of the bullet plus mass of the block times G times H. Gives you that one here. This is just mgh. The initial kinetic energy, 1/2 mv squared, has to equal mgh. That's the initial kinetic energy of the bullet block pair after impact. If we have the maximum potential energy equals the initial kinetic energy. The initial kinetic energy you can calculate by that equals 1/2 mass of the bullet plus mass of the block square. So 1/2 m mass of the, where m is mass of the bullet, mass of the block, times velocity squared equals this. So that equals mgh, or velocity is just equal to √2gh. Okay, so we have h, so we get this velocity. Linear momentum of the bullet block pair after impact. Well, now that you got the velocity, you can get the momentum. That gives you the initial momentum of just the bullet. It has to equal the linear momentum of the bullet block pair after impact. They have to be equal. Okay. Then we can get from that momentum, now that we know the momentum and mass, we have the initial velocity of the bullet. If you're in the real world, can somebody tell me, if you had to do in the real world, can you tell me what 3 measurements, all sensitive to possible error, do you have in here? Just measurements, not, we didn't shoot the gun at a proper angle and things like that. What 3 things are you measuring in this experiment?
Velocity?
You're not measuring the velocity, you're determining the velocity based on measurements. What are you measuring? If you were in a lab and taking these measurements, what would you be measuring? I know you guys know this, so put yourself out there, risk saying something wrong. Imagine you're in a lab and you're
Angle.
Okay, that could be one thing on one type of but if I were doing this in the lab, what would I have to measure? I'd have to measure the height the pendulum goes to, right?
Yeah.
Now, maybe I would have had a slider and measured the length to determine the angle, to then determine the height. I'd have to measure the length of these strings. I'd have to know the length of the pendulum, perhaps. Okay, here we're just measuring a height. That's not very practical in the lab to have done just measuring the height. I have to measure the mass of the block. There's uncertainty in my mass measurements. I have to measure the mass of the bullet. There's uncertainty in the mass of my bullet measurements. You should think about how these different uncertainties would come into your uncertainty in your velocity measurement. Okay, I want you guys to think about how you would do these in real life. Very hard to write up a lab that can actually, judge how well you're doing that. But I want you to think about these things. If I've got to do this measurement in the lab, I've got to measure the height. I've got to measure the mass of the bullet, and I have to measure the mass of the block. Those are the 3 things that go into my formula here. I'm going to use height here. Mass of the bullet, mass of the block. That gets my initial potential energy. Okay. I also have mass of the bullet, mass of the block here, but they can cancel out. To get my V squared is 1/2 G times H. So they cancel out. So to get my initial kinetic energy, I really I can get my initial kinetic energy is only subject to error in the height measurement. Because my mass of the bullet, mass of my block don't matter. Now I'm going to get error because of friction, but we're ignoring friction right now. Now, I've got error though here in this mass measurement for my momentum. So I've got error in my momentum. I've got an error in my velocity due to my error in height. I've got error in my momentum due to the error in my velocity, plus my error in my mass measurement. And since I have error in my mass measurement of the mass of the block, I've also got error in the mass measurement of mass of the bullet, because my velocity of the bullet is going to equal to mass of the bullet plus mass of the block times the velocity after impact divided by mass of the bullet. And if we wrote this out with regard to this, and if you remember what we showed in the lab earlier today, we have potential energy is equal to mass of the bullet plus mass of the block times GH, and kinetic energy after impact, this is max. Kinetic energy after impact was 1/2 mass of the bullet, mass of the block times GH, and my potential energy at this point is 0. So 1/2 mass of the bullet plus mass of the block times V times GH times V after impact squared times V after impact squared is equal to mass of the bullet plus mass of the block times GH, or V after impact is equal to square root of 2GH. Okay. Now, momentum before impact equals momentum after impact, which is equal to, which then leads to mass of the bullet. Velocity of the bullet is equal to the mass of the bullet plus mass of the block. Velocity after impact, or velocity of the bullet, is equal to mass of the bullet plus mass of the block divided by mass of the bullet times square root of 2GH. We're determining mass of the velocity of the bullet. So my errors in that, my measurements are mass of the block, mass of the bullet, mass of the block, mass of the bullet again, times 2GH. There's my other measurement where error can be. Okay, now, of course, there can be errors in other places as well, and think about those things, such as twisting of the block. Some of the energy could go into twisting of the block if the bullet doesn't come in straight. Some of the error can come into friction, could be in friction, in the strings, air resistance, okay? There's other places for sources of error. So you're just simply going to go through these for these 9 elements, and the net result is you want to get the initial velocity of the bullet. So that's all you're doing in this lab. Now, what percentage of the bullet's kinetic energy is lost? And I want you to calculate that for 2, 4, and 9. We have 3 different masses of the bullet, 3 different masses of the block. Okay. What
Is that only 2, 4, and 9, or the whole thing?
in trials 2, 4, and 9? So trial 2 is this trial. You're going to have this line. I want you to know what percentage of the bullet's kinetic energy is lost.
Oh, okay. Okay.
Okay. So how much kinetic energy is lost? Okay. What is the impulse on just the bullet in trial 6? So just trial 6. What is the impulse on the bullet? Impulse is the change in momentum of the bullet, not the change in momentum of the system. The change in momentum of the bullet. Okay, this asks for the impulse on the bullet. And you must include the direction or the sign. Was impulse is a vector? Is the impulse assume that the velocity is in the initial velocity is positive because it's going from left to right? And make sure to include the sign. And remember, you're looking for the change in momentum of the bullet only, not the change in momentum of the system. What is the impulse on the block in trial 3? That's the change in momentum of the block, not the change in momentum of the system. You're going to assume the block is 10 centimeters long, 5.8.4. You're going to assume the block is 10 centimeters long. And the bullet comes to rest at the exact center of the block, while being decelerated uniformly during the entire impact. Determine the average force exerted on the block during the impact in trial 3. What assumptions, if any, did you make in your calculation? Okay. Now, basic assumption, one of the assumptions I make is that the block doesn't move, that the block and bullet pair don't move at all, don't actually move during impact. They move a very small amount. Okay, so the first assumption I'm going to make is the block isn't moving. Now, I ask you to get the average force exerted on the block during the impact in the trial. Does anybody have any idea how they're going to do this? I need someone. So what if I do my force is just equal to mass times acceleration, right? So I've got my force equals mass times acceleration. Okay. Now, I could do, my average force is equal to J over delta T, or it's equal to delta P over delta T. That's my average force, right? But I don't know what delta T is. I have no idea how long this impact takes. But it'd be interesting to know how long delta T takes. And what else do I know? What equation can I possibly use that doesn't have time? Well, I can do V final squared equals V initial squared plus 2A x minus x0. Right?
Yes.
But do I know how far the block moved during impact?
When you run the simulation, wouldn't you be able to see how far it moves?
Well, in principle, but it's going to move a very small amount. Do I know how far the bullet moved during impact?
Find out by the height the block rose up.
Well, how about I just measure it? In fact, on here, I said, assume the block is 10 centimeters long and the bullet comes to rest at exactly the center of the block. Will be decelerated uniformly. Right? So x minus x0 is 5 centimeters. V final of the bullet is equal to V final of V after impact. So V final here is just V after impact. So V after impact squared equals V initial squared plus 2A times 5 centimeters. Right? You following so far?
Yeah,
Yes.
Okay. V initial, you calculated. This is V initial of the bullet. You calculated. It's in your table. Okay. You pick, I would pick trial 3. I meant to say trial 3 here, but I didn't. Okay, so you got to pick which trial, but pick trial 3 or trial 6. Okay, it doesn't matter. Pick one of the trials. I'll have to calculate it for all of them. And you'll have to indicate which trial. There's different forces depending on the trial. But you have the initial velocity of the bullet calculated here. So I can get my acceleration is equal to velocity after impact squared minus velocity before impact squared. It's just velocity of the bullet squared divided by 2 times 5 centimeters. Now you gotta make sure to put that into meters. And this is gonna give you a negative sign as it should, because you're decelerating. It's in the negative direction. And this is its average acceleration. We're assuming it's decelerating uniformly. So F on the bullet due to the block equals mass of the bullet times A on the bullet. Right? Now, what does Newton's third law tell us?
the object stays at rest until another object acts on it.
That's Newton's first law. What does Newton's third law tell us?
Where are the mass for the block?
What is the mass? What about the mass of the block?
Zero? I don't know.
The mass of the block isn't 0. What is Newton's third law?
That the like a force of an object A, when it exerts a force on object B simultaneously exerts a force on object A.
Exactly. So the force on object A exerted by object B is equal in magnitude and opposite in direction of the force on object B exerted by object A. So FAB equals minus F sub BA. F of A on B equals minus F of B on A. This is Newton's third law. Don't forget these. You're going to need these sort of laws, and you need to remember these sort of things in the exams. Our labs are trying to reinforce some of this. So I ask you in 5.A4, why this is moving this way. Okay, so I ask you in 5.A4, the force exerted on the block during impact. But I don't have the information to get the force exerted on the block during impact. At least it's not obvious that I have the information, but it is obvious that I have the information that the force exerted on the bullet by the block during impact, because I have a distance that it came to a stop. I have the bullet's initial velocity. I have the bullet's final velocity. We've recalculated that. That's the bullet's moving at the same speed as the block after impact. So that's the bullet's final velocity. It's moving at the same speed as the block. They're moving together. So I can calculate the acceleration on the bullet. Different than the acceleration on the block. They're very different in mass. But the forces are the same. So I calculate the force on the bullet due to the block, and now I can get the force on the block due to the bullet by using Newton's third law. It's just the same. It's the same magnitude, opposite direction. Make sure you give the directions on the answer here. So I'm giving you a little bit of room to work it out. And the final thing is identify 4 sources of error that should be accounted for in determination of the bullet's initial velocity, assuming you are making the measurement in the lab using physical hardware. We have already mentioned at least 5. Okay, so we mentioned 5, at least 5 in the lab. Okay. So you should have no problem answering this. That's all there is to this week's lab. I want to enforce. I do not want to do this for you, but I want to enforce. You know, I don't like doing the lab for you, but I really want to enforce here. What are we using here? We're going back to our early chapters in some of this. You know, with this question, I give an assumption. I gave the distance that it stops over. Now we're assuming the block isn't moving during this. Okay, because the stopping distance I'm taking as the 5 centimeters. The block is actually moving a tiny bit. You can get now the time of this impact. If I have now the average force, and I could have put some more problems on here, probably should have. How much time did the impact take? If that took that amount of time, which you can do that, if you have A, if I have A, then F average on the bullet a bullet on the bullet is equal to mass of the bullet times A of the bullet, but it's going to equal to delta P of the bullet over delta T. So delta T is going to equal to delta P over mass of the bullet times acceleration of the bullet. Okay? So for your own interest, you should see just how fast that event happens. Okay, because the acceleration of the bullet is going to be quite high. So you're going to find a small number here. Okay, if I take that number, then I can get an estimate to how far the block actually moved. But first I assume the block doesn't move, so it's only 5 centimeters. Now I can use that delta T and the force on the block and the mass on the block to determine how far the block actually did move during impact. Okay, these are some questions I didn't ask. Okay, maybe, you know, next year's class we'll get asked those questions if we're still doing things online. All right, but from this, we can get the time of impact. How long did the impact take? Which is an interesting number to get. All right.
Okay.
Okay, teacher.
So you guys should play with these labs a little bit and look at, I view these as some of the interesting numbers to get. I view these as, you know, something that you want to kind of get out of this. Take these labs, do a little extra with them, use them to help understand the chapter. Ask yourself some questions on it. All right.
All right.
Okay.
Professor, I had a question.
Yes.
For like when we're doing the table, you said, or at least from my understanding, you said that to calculate the initial velocity of the bullet and block pair after impact, we use the equation that's like a 2 times the mass of the bullet and the mass of the block times the gravity times the height.
Okay, let's go back to that. Here we have that again, okay?
Mhm.
You're measuring the maximum height of the pendulum. Okay, that's a measurement.
Mhm.
So the maximum potential energy of the bullet block pair is the mass of the bullet plus the mass of the block times GH. That's our definition of potential energy. We're
Got it.
taking our 0 point as the bottom. Since we have conservation of mechanical energy, that's equal to the kinetic energy immediately after impact. We're using conservation mechanical energy. No non-conservative forces are acting. So then this value here, the maximum potential energy, just equals the kinetic energy. But the kinetic energy is 1/2 the mass of the bullet plus the mass of the block times the velocity after impact squared. So I can use this with the kinetic energy. So I know the mass of the bullet, mass of the block, and I know what 1/2 equals. So I can write that the velocity, therefore, so I write that these two are equal. This is the kinetic energy right after impact. This is the potential energy at max height. So I can write that the velocity of the bullet, the velocity of the bullet block pair right after impact is square root of 2 GH. So now I have this column. It's just equal to square root of 2. It's equal to the square root of 2 times G times the value that's over here. Or it's equal to, which is, so you can just calculate it right away. Okay, you don't need you didn't need these two columns. Okay, to calculate this column. I gave you these two columns to walk you through to this point here. So you're getting the kinetic and potential energies. All right.
Got it.
That's the velocity of the bullet block pair. Linear momentum tells me that the mass of the bullet plus the velocity of the bullet before impact is equal to the mass of the bullet plus the mass of the block times the velocity of the pair after impact. That's conservation of linear momentum right here. So I gave you the initial velocity. So now I walk you through this. This is the linear momentum. These two columns are equal. The linear momentum of the bullet block pair after impact has to equal the initial momentum of the bullet. So these two columns should have the same value in them. These two columns should have the same value in them. It's just walking you through this step by step. And if you know the momentum of the bullet and you know the mass of the bullet, you can get the velocity of the bullet because momentum is equal to mass times velocity. So pendulum, the height of the pendulum gives you the potential energy of the pendulum. The potential energy of the pendulum gives you the initial kinetic energy of the bullet block pair. So the bullet block pair is the pendulum. Okay. The maximum potential energy of the bullet block pair gives you the initial kinetic energy or the maximum kinetic energy of the bullet block pair. Okay, they're equal. This is the maximum potential energy. This is the maximum kinetic energy. You have the maximum kinetic energy, you can get the initial velocity. So if I have the initial velocity, I can get the momentum. Okay, my momentum is just the momentum after impact is just equal to the mass of the bullet plus the mass of the block, capital M, times the velocity after impact. So I have the momentum. So right after impact. So that has to equal the initial momentum of the bullet, conservation momentum. And if I have the momentum before impact, this is just to the bullet. Okay. Then I can get the velocity of the bullet. That's how we get the velocity of the bullet. This column here, you can calculate using this expression. You can calculate that this value here, and I'm circling here, is equal to the value in this column. You can get V after impact from that. Or we can just use V after impact is equal to square root of 2GH, which is what we get when we simplify this equation here. So V after impact is just square root of 2GH. Conservation momentum to get the initial momentum of the bullet and hence the initial velocity of the bullet. And that should just equal, this is the velocity of the bullet before impact is this formula here. Okay, because I can just get this in, all in one simple formula. Mass of the bullet plus mass of the block over mass of the bullet times square root of 2GH. That's the velocity of the bullet. Make sense?
Yes. Thank you.
Okay. This is, the table is about walking you through that and seeing the different pieces of information you can get out of it. This one here is the only one in there that I felt was even, this one here is the one that was asking a stretch. You know, this was the stretch problem, the bridging problem, going back to, well, I know the force is the impulse over the time, or delta P over delta T. Impulse is just delta P. Okay, so I know the force is, the average force is delta P over delta T, but I don't know delta T. But I can measure, it's feasible to measure where the bullet ended up in the block. And I'm going to assume that happened over a short time. So that I'm going to have an error because the block is going to move. Okay. So instead of 5.00, you know, I have 10.0 centimeters, but I don't know what the distance is. So we went through here. I'm going to assume the block doesn't move for this calculation. And for this calculation, you know, we can just go through this. We can go through this for one of them. You're not allowed to do number 8, say. I'm going to do, say, number 8. You're not allowed to do number 8. Okay, so the mass of the block is going to be 4. And the mass of the bullet. So I'm going to reset. And I'm going to hit fire. Now I'm going to measure 8. I'm going to measure my height. That seems a little high. That seems about right. I'm going to call it 1.10. Now let's see if I can edit on here. Let me print this page. And current page. Do current view, make it bigger. Okay, I'm going to print out this page so I can write on it. Give me 1 second to grab it. So I'm doing line 8 here. Okay, so I'm going to take this over to this side. And I'm saying it's 1.10. 1.11 looked a little too high, 1.09 looked a little too low. So I'm going to say it's 1.10. That's in meters. Okay, so my initial, my maximum potential energy is M, which is going to be 4.1 That's 4 plus 0.1 G, and H is 1.1. And I get 44.2. I have 44.2 joules. So my initial kinetic energy is 44.2 joules. Now I'm just going to do root 2 GH for my velocity. So I have 2 9.8 times 1.1 times square root is 4.64. So that's my initial velocity. My momentum, 4.1 times is 19.0. Now I'm going ahead and I'm not worrying about the fact I'm going to have round off there. You should get better than that. So the initial momentum of the bullet is 19.0. And now if I divide that by the mass of the bullet, I get 190. Now I'm going to show initial velocity of the bullet and see if that's correct. 191.25. So I told you I was going to have round off error. Okay, and I intentionally just worked this through with round off error. You shouldn't do it with round, and I've got error in my measurement here, but I'm not so far off. I'm less than 0.5% off. Okay, or I'm right around 0.5% off. I'm not so far off from this. I've got some calculation round off error. Was this early 1.1, 1.09, 1.11, probably closer to 1.1. Okay, if I put in, maybe it's closer to 1.11, because that'd be about a 1% difference. If I look up here, maybe I should have used 1.1. If I reset this here and take it down to the bottom, yeah, it looks like that's completely covered. So maybe I should have used closer to 1.1. Okay, but I told you you had to recognize the error. Now, I've got a velocity of the bullet now. I started at, so now, question 4.84. Or 5.84. So I've got delta X. Come on, why are you doing this to me? Delta X was equal to 0.05 meters, 5 centimeters. Okay. I add V initial of the bullet is equal to 190 meters per second. V final of the bullet, the bullet final, was equal to 4.64 meters per second. Okay. V bullet final squared equals V bullet initial squared minus 2A delta X. So A is equal to V bullet final minus V or plus 2A delta X, V bullet initial squared divided by 2 delta X. So this is 190 equal to 190 squared minus 4.64 squared over 2 times 0.05. And that equals 1 0 squared 4.64 squared minus, this should have been a minus sign. This is I'll put a minus sign in front of here because I put, this was the initial and this is the final. I wrote them in the wrong order. So that's 36,000. 2 divide. And 5 centimeters, 0.05 divide. So A is equal to minus 361,000 meters per second squared. Pretty high deceleration. So V is equal to V0 plus AT. So T is equal to V minus V0 over A, which is equal to, V final was 4.64 minus 190 divided by 360,000. So T is equal to, inverse that, my 360. I don't have the minus, and this is a minus sign. 190, enter, 4.64 minus times, and I'm going to multiply it by 10 to the 4. I want to see more significant figures. And it's equal to 5.14 times 10 to the minus 4 seconds. Or 0.5 milliseconds. So that's how fast it happened. I also can write my force on the bullet. My force, on bullet by block equals mass of bullet times acceleration, which is equal to 360,000. And again, I have round off in here. 0.1, I have it at 0.1 times, so I have 36,000 newtons. And that's the same force as on the block. Okay, but now I can take my acceleration of the block and say, does this make sense? Okay, because it only happens for a very short time. So the acceleration of the block, so the force on block is equal to 36,000. This is minus 36,000 is equal to plus 36,000 newtons. I'm doing trial 8. So my acceleration of the block is equal to this force divided by the mass. But I've got to divide, so I'm going to assume that that force is acting just on the block. the whole time and not dealing with both of them. So I'm gonna divide this by 4. So it's 9,000 meters per second squared. I'm going to multiply it by my 5.14 times 10 to the minus 4 exponent 4 change sign times. So V is equal to AT for the block. It's going to be block. And that's going to equal 4.626 meters per second. And that's very small error with the 4.64 I got here. So there's very small error introduced due to the block moving. This gave you time of interaction, 0.5 millisecond, 500 microseconds. There's a lot of interesting stuff you can get out of a problem like this. I didn't ask you for this in the problem. I asked you for the force on the block. I did not ask you for the acceleration of the block. I did not ask you, to prove that these come out the same, but look, this all works out about the same. We have small error in working these out. We have round off error in the calculator. These all worked out about the same. This was a nice 4.626 with round off error, 4.64 had round off error. Those look in all pretty nice agreement. 0.01 out of 4, that's a, let's see, 0.01, 0.04 would be a 1% error, so it's about 0.25% error. That's pretty good. We have our biggest source of error in this thing is the measuring of the height. And even that was a relatively small error. Okay, but you can get a lot of stuff out of this. And you can work it backwards to calculate and see whether things all make sense and hang together. But you should now see exactly how to have measured the force on the block versus the force on the bullet. So that the force on the bullet to get this acceleration, but that's a heck of an acceleration on the bullet going into that block to stop it in 5 centimeters. And it's a lot of force as well. Okay, any questions?
Oh, not now. Bye.
No questions, Professor. You pretty much explained it and put it in perspective, the equations and how to use them for the table. Thank you.
Okay, and that's what we want to do is enforce on the lab here some of the stuff that you've done in the class. But the problems, some of the problems in the homework are harder. I just want you to, and some of the problems on the exam are harder than this one. But you got to see how you use these equations and how you work through problems like this. All right. I'm going to stop the recording.